So good day everyone, good day sir. My project will be all about project number 6, which is finite automaton simulation with regular expression. Its description is to develop a program that simulates a finite automaton, whether it's DFA or NFA, and accepts or rejects strings based on a given regular expression. And the RE, or the regular expression, should be converted into an automaton before string recognition. So for the instructions, we are instructed to convert the regular expression into an NFA or DFA. Next is to simulate the automaton and check if the input string is accepted by the automaton. C. Implement basic regular expressions like union, concatenation, and clean star. Provide examples of strings that should be accepted or rejected, and create a Python program that simulates the finite automaton and checks the string acceptance, the documentation, and then the video. First, we should start uh, showing how to convert the regular expression into an NFA. So in this program, I'm going to be solely focusing on the converting of the regex, as I will try to shorten it now. And then I will be focusing on making it into an NFA. So before I start showing my code, I want to show this simple flowchart of how the program works. So first, the program accepts a regular expression as an input, and then that input will be standardized so that the operators are all present. For example, given given AB, I want to equate this into a equation, or the regular expression. I want to standardize it, and so it looks like A dot B. And so every time there's no operations in between two symbols, the standardization will place a concatenation symbol or operator. After standardizing the regular expression, we want to convert it to a postfix notation so that it will be ready for the conversion to an NFA. So the postfix notation's purpose is to eliminate the pairs of parentheses. So it also tries to group the two symbols, the groups two pairs of symbols, and then it maps to an operator found at the right side of those two symbols. So for example, let's take the example above here, the A dot B. So after converting it to postfix, it would look something like AB dot, which means the A and the B will be applied to a function of dot. For more complex functions such as A plus B, it will be just similar to the dot notation, which can just have AB plus. But for example, if you have something complex like A dot B plus A, this will equate to A and then B plus A, I mean BA plus and then a dot, which means that BA will be applied to the operator of union, and then it will also that will count as a single object or a single symbol, and then next the A and then the other object will be concatenated all together so that it will equate into A dot and then B plus A. And so next we're gonna convert that postfix notation into an NFA finally. In this function, we're going to just read every symbol. So if it finds a symbol, it will create an NFA fragment. And then if it reads an operator, we're just gonna connect those two fragments together. And after creating an NFA based on the regular expression that the user can input, we can also input strings, or we can just place input strings to validate whether or not an input string is valid based on that regular expression. And then the program will also output a corresponding transition table based on the regular expression. Anyway, let's move on to our code. So first, this is what the let's first look at our main main file. So for example, just to have a simulation of our code, let's for example, let's do an A B for a regex, which means A dot B. And so if we run this code, or let's put a test string as our input. So if we run this code, it should look like this. As you can see, our regex is AB, and then after standardizing and then postfixing, the postfixing will output as AB dot. And then this is what the transition table looks like. We have three states, which are Q0, Q1, and Q3, with two alphabets, which are A and B. And then we can see that Q0 maps to Q1 inputted with A, and then Q1 goes to Q3 inputted with B, and then Q3 is the accept state. And then we can also see that the AB is our test string is accepted. But if we put a string such as BA, you can see that it is rejected. So moving on to the explanation of the code, let's first start with our class, which is the NFA class. So the NFA class basically has the properties, a state set, a start variable, an accept states accept set, or let's just say a set of accept states, and then the transition table. It will be the transition table will be implemented using a graph by using dictionaries, of course. And then for the first function, we have an add state. This just makes another state into our NFA. And so anyway, we have our add state function. In this add state function, we're taking the name, and then we have two more arguments, which is the is start and the is accept argument. This just determines whether if the state is an accept state or a start state. And so when calling this function, we're just basically adding or initializing a new state, in which if it's an accept state, then we set it as that. If it's an accept start state, we just set the self that start property or attribute to it. And so when we create the state, it will add it will append that specific state into our transition table, such as this in this function. So if that name or if that state is not in the self net transitions, then we will just append that and then create a dictionary within that state. So next up, we have the add transition function. In this transition, we're taking a from state symbol and a to state argument. So we're just creating a connection in between the from state to the to state given a symbol using this function of set default. So basically, in the self dot transitions, we're trying to access the from state. So this will try to refer or return the dictionary of the from state. And then the set default function basically just appends this to state if there's no set found in that corresponding key, then we're adding just an empty set. Next up, we have the display function of the NFA. This basically just displays the NFA transition table, and it looks something like this in the results. So we're just basically storing each symbol in a sorted array, and then we're creating a header by joining all of the symbols, and then we're just iterating through the whole states, and then just uh, appending or just joining each destination to its corresponding state. And then for the simulation, we're just taking every character of the accept string and then checking if there is a let's say a path that leads toward an accept state. So moving on, let's go to our standardized function. And this function, we're just trying to put a dot in between in between symbols that don't have an operator. For example, if we input AB, the standardized function will return a dot B. And if it's like ABBA, then it will output something A dot B dot B dot A. And it will something like this. So we have our result operators and previous. So for each character in the regular expression, if the previous is not none, meaning if there's no input or no value, then we're just reading if it's a closing parenthesis, and if the previous character is a closing parenthesis, or and if the character is like another opening parenthesis, they were putting a dot. Basically, it just says if it's a symbol, and then if the previous character is also a symbol, then we're adding a dot. If it's a closing parenthesis in the past, like meaning the previous, and then if the current symbol is a opening parenthesis, then we're placing a dot. Again, if it's in between two symbols, we add a dot or a concatenation. If it's closing parenthesis, then in an opening parenthesis, then we add another dot. So that's basically what this function does. And then next up, we have the postfix function, which takes in another regex input string. So in this, the difference between this and the standardized is where we have the operator set as a dictionary, which has its own value of precedence. So the purpose of this is to again eliminate the pairs of parentheses by making it in a notation of calling it was called reverse Polish notation. So the most important part of this function is these two functions or these two conditional statements, wherein if it finds a closing parenthesis, it will iterate through every single operator found, and then it will just append it to the result list. Else, if it finds an operator, it will check if that operator's precedence is greater than or is the current operator is less than the past. So for example, operators of stack minus one, meaning we check the top of the stack, and if it's greater than the current operator, then we append that result or we append that operator to the result. If not, then we just append that operator to the stack. So next, we have our NFA or Regex or postfix to NFA. So in this function is where all of the magic happens, where we create a NFA based on the regex by using the postfix version of the regular expression. So this is a bit hard to explain a without a pen and paper, so I'll try my best. So basically, for each and every element or each and every string in the postfix string, first we're trying to check if it's a alphanumeric string, meaning if it's A to Z and then 0 to 9. If so, uh, we're just creating an NFA fragment using this function or these three lines where we create a start state like so, and then we create another finish state, and then we just add a connection in between using this function. And then we're adding it to a stack. Next up is our concatenation function. So for example, let's try to simulate something. So let's say we have regex of a b dot, which is a dot b. So first it will read a. So if it's a, meaning it runs this code, it will create an NFA fragment of a, wherein q0 goes to q1 given a, and then for b we have q3, I mean q2 to q3. Looks like this. So let's say we have an a b dot. So for our first NFA fragment we have q0, and then given an a, it'll map to q1. So next up, after making our NFA fragment of a, let's just assume that this is the start state and this is the finishing state. And so we also have to we're gonna need to make another NFA fragment for the B. So we have Q2 to Q3 for the NFA fragment. So this is what it looks like in the code right now. So just ignore it. So after creating those two fragments, next up we have the third element, which is the concatenation operator, which is the dot. So let's go back to our code and read it. So first, since we're appending those two or these two NFA fragments to the stack, we have to access them somehow. And so we're using the dot pop function to get them, and then we're assigning it to a variable. So in this part of the code, which this triple for loop will be an common common line or common lines that will be present in this function. So basically, what this does is it takes in the accept or like the accept state of the of the first NFA, and afterwards we're also taking the start state of the right NFA. So for example, this is our left NFA, the A1, the Q0 to Q1. So we're taking the accept state, which is Q1, and then we're also taking the start state of the Q2 in this part. So we're taking Q2. So what we're essentially doing is we're just replacing the destination or the destination state of Q2 and then applying it to Q1. So instead of Q0 going to Q1 and then Q2 going to Q3, Q2 will be Q2 will not be accessible basically because it will just connect Q0 to Q1 and then Q1 to Q3. How does it work? So basically, for each symbol and destinations found in the start state, and then for each destination in that destination list, we're adding that destination to the first NFA. So for example, Q0 to Q1, A, and then Q1 to Q3 will now be connected. So if we look at it as a table, it looks like this. So for example, we have, let's just take Q1 and Q2 for example. So we have Q1 doesn't have any transition states, leave it as blank, but Q2 given B it goes to Q3, right? So for each accept states in less NFA1, for example, so it's Q1. And then for each symbol and destinations in NFA2 transitions, NFA2 started items, basically Q2, each symbol meaning AB, and then each destination meaning Q3 in that symbol, it will iterate each and every transition or each and every state in that specific symbol, and then we're adding it to the NFA1. So meaning from Q2, we're like basically copying that and then applying it to Q1. So basically Q1 now has a similar transition table as to Q2 to connect it. Next, we have the union. The union is a bit more complex, but it's in a similar fashion to concatenation, but just a different way of connecting, or just a different process. So basically, we're still making two fragments again, Q0, Q1 with A, then Q2 with Q3. What we're doing is we're just making another start state, and then we're connecting it to the accept states of the last two NFA, like so. So A1 is going to be with the A, then Q4 to Q3 with B. Again, this is our accept states. So in this code, again, look, we're making a start state. We're also taking both of the NFAs that we created. This is basically NFA 1 and this is NFA 2, or I think it's vice versa. So we're copying the states of those NFAs like so, and then we're just connecting them both like how we did in the first one. Now for our clean stars, this is the simplest. We're just basically making an NFA wherein there's two states, Q0 and then Q1, and then depends on what the symbol is. For example, A star, we're just doing Q0 to Q1 using A, and then we're pointing Q0 to itself with A, of course. So that's what it looks like. And so that's basically all of the functions it explained. And so if you run this code, it actually works in complex regex, which has two or more alphabets. So we could take like a complex regular expression, for example, names like Rujz and John, or Rujz or John. Then we could have test strings with full names also, and see what if they are accepted or not. And so if we run this, as you can see, the Rujz is accepted because it's Rujz or John. The blank test string is also, I mean, it's not accepted. John is accepted because it's Rujz or John, and then Andre is rejected because it's not inside it's not inside the regular expression. So that's basically everything. Thank you.